So I think it has started recording. Yeah, it has started recording. Cool. So okay, let me just clear some things from here. Yeah. Okay. Hello and welcome everyone. This is going to be this is supposed to be a series of lectures in which we will be discussing some core concepts of machine learning, which will be, I hope that it is useful in placements as well as in academic your academic career if you want to pursue that. The way I have planned, these series of lectures is that uh, I want to first of all I want to just make so I want to take a mathematical approach rather than a hand wavy approach. The reason being that there are a large amount of lectures that are available online, which do these kind of hand waving, and so I mean there is abundance of those types of lectures where you can just people will hand wave few of the concepts. They will write something and they won't explain it fully and just go over it without going into the depths. But in my opinion, those are the kind of things that makes you different from the guys who actually know things in depth. So I feel that it is better to have a in-depth mathematical knowledge of things, and just make sure that none of you think that it is just like few people say it is just model.fit. Okay, so there is a trend that you can just fit you there is sklearn and things like that where you can just input the data, you have an algorithm, you do algorithm dot fit data and you get a model out of it. So I don't think that is a good approach to learn machine learning. It takes the joy and fun out of it. So let us try to at least have a mathematical approach, and we will see like why is it necessary. And actually whenever you encounter problems in real world, it's not the dot fit that is going to help you. It is most probably maths that is going to help you, or some bug in your code, of course. So let us get started with it. So earlier I was thinking, okay, let me write something. So let me just know that this is video, whatever I am writing is visible to you. Okay, this is visible, right? You are able to see this lecture one that I have
Yeah, yeah,
written
yeah,
here.
yeah. Yeah, it is visible. Yeah.
Okay. Okay, yeah, that was just a sanity check to you. Okay, cool. So earlier I had thought, to take since so okay, so this will be basically a introductory basics for ML. So it won't be, like we won't go into like deep dive. So we won't like dive into ML directly. We will, just see the tools that are required to understand ML, and particularly what I had thought earlier is that we will, go over some probability primers. Okay, I don't think that is even a word. So I think it's primer on probability. Primer on probability. So just to massage our brains with whatever we have already learned, maybe in bit more depth detail. Second thing that was I was thinking was information theory. Information theory. Okay. And third thing that I was thinking was optimization. So these were like the three things that I was thinking to cover in this first introductory lecture. But then I thought that perhaps doing optimize. So, okay, just a second. So perhaps doing I don't. I'm not sure if we will be able to cover optimization today itself, because optimization requires some background and things like that. And also like most of the optimization that we are going to use in machine learning is known to everyone anyways. The only thing that I like tried that I think people don't know is something called constrained optimization. Constrained optimization, which I was thinking to cover here. But okay, I mean, I thought that also constraint optimization, we will be using constraint optimization only in SVMs when we study SVMs. Okay, and some topics I don't know. It can pop up anywhere, so it's really not good for me to tell that okay SVMs is only where it is used. But yeah, so I think today it would be better if we like stick to these two topics. Okay, probability and information theory. I think probability most of you know what it is, but nonetheless let us go over it so that people who might be bit slack on probability will kind of remember what it is, and like just to make sure that we are on the same page from the next lecture onwards, we will do some probability, and then we will perhaps I don't know how many of you are familiar with information theory, but I think that is something that pops up everywhere in ML, and nowadays it's like daily language for us researchers who are working in it. So I thought it would be a nice opportunity for me to at least give you some introduction to it, and like get you familiar with these terms like entropy, KL divergence, mutual information, and things like that. So yeah, this is the plan for today. If you guys have any question, okay. So yeah, I mean, so okay, so like okay, so let me ask you if you have any questions still from on this part, that okay, is there any ambiguity here? Maybe I will address them. Otherwise, I will tell you what is my vision for this series of lecture, like how much I intend to cover and things like that. But before that, let me ask you if you have anything to ask.
No, no, you can go on. We are clear on this part.
Okay. So this is sort of logistics also. Okay. So I was thinking, what are the topics that we should cover? Topics that we should cover. Question. So my idea, okay, since this is an ML theory class, these are ML theory lectures, so I was thinking to like first, okay, today's lecture will be fundamental, so anyway I am skipping that. So these are the topics that I broadly intend to cover. First is okay, so first is like Bayes classifier, Bayes classifier, and maximum likelihood estimation. Second is expectation maximization. Okay. Third part that I intend to cover is what else? Expectation maximization, base classifier. Then I guess we have uh, parametric and non-parametric models. Parametric and non-parametric models. Okay. Then I think we have linear models. Uh, linear models. Then I think after linear models, we can see some multi-class extensions here. Multi-class extensions. Okay. mm, and I think after this, I think it would be support vector machines. Machines also called as SVM. After this, so I think this itself is like a lot. Okay, but if in case we get we are, we have some time left, we will cover what is called as neural nets, neural networks. Okay. and and this is something new that I have also learned very recently, and I wish I knew it, way before recently. Okay, I mean, I wish I had known this thing like long back, and which is neural tangent kernels, which is also called NTKs. Okay, so I like these are broadly the topics that I intend to cover. Uh, as you can see, most of these are like like first course in ML kind of topics. But nonetheless, the first course in ML that I have seen on YouTube, most of them at least, few of them are there which are actually in depth and quite clear, but uh, most of them are bit hand wavy, and they don't explain why a particular algorithm works, if it has to work, and things like that. So these are broadly the topics that I think would be a nice approach to would be a nice vision for these lectures. Okay, so here, do you have any questions, or do you have any requests as to say, as to okay, can you also cover this or that kind of stuff? If those kinds of things are there, then you can ask right now.
Yeah, I think as we go on, then
Mm-hmm.
maybe we are not that much familiar about ML. So like, if we find
Mm-hmm.
new stuff, we'll ask you if you are if we have time left, and
Okay.
you know,
Yeah, yeah. Okay, so okay, I think that is also good. Yeah, so I also encourage you to read about this stuff. If you have any doubts, we have a group. I think you can always ask questions there. I will try to answer it there, or we can take those questions in these lectures as well. No issues there. So
yeah,
yeah, it's a good I think practice to keep reading about some topics that you are interested about, and kind of just, if you think that okay, this is some topic that I think is not being covered in this lecture, then you can can be if those topics can be accommodated here or not. Okay.
right, right.
So okay, so I think that is a good vision, and I think we can get started with the actual stuff now. Okay, so let us start with
Yeah,
probability theory. Okay. Okay, so first thing that we have to cover is what is called probability theory. Okay, so okay, what is exactly probability? I think most of us are, like we know what probability is, but in some abstract sense, that okay, it is. So I am sure that it is I mean, that probability has something to do with chances and uncertainty in something. So, for example, if I toss a coin, it is going to be either heads or tails, but you don't know exactly what it is going to be. So there is some uncertainty involved here. Okay, so you do something, there is some uncertainty involved in whatever you are doing, and you want to you want to build a tool, so to say, to analyze such things, such phenomenons. Okay, so probability theory provides you those tools. Okay, probability theory is that tool that allows you to kind of handle these situations. Okay, so but nonetheless, who came up? So the probability theory that we see today, okay, is, how has it evolved? There's a long history, but let me mention name of one person. If you don't like probability theory, this is the person who came up with it, and you should curse him. So his name is Kolmogorov. Okay, Kolmogorov. So Kolmogorov was the guy who came up. So okay, so probability theory is not something that Kolmogorov came with. Probability theory is it's very ancient. There are evidence that Greek and Egyptian civilizations, or even Mohenjo-daro and Harappa civilization also had this idea of chances, and there used to be some gambling that people used to practice. And so the idea of chances, randomness and things like that is not what Kolmogorov came up with. It is very ancient, and people have been familiar with it since, I don't know, like long back. Okay, but what Kolmogorov did was, Kolmogorov came up with a systematic okay, so let me write it. He came up with a systematic way to study these things. Okay, systematic way to study uh, quote unquote random things. Okay, I am just writing it vaguely here. So okay, so first question that should come to our mind is, okay, so there are, the first thing that is involved, that we should know is, probability theory always, probability, so to say, is also always associated with a, what we call as random experiment. Okay, what is random experiment? So whenever we think of probability theory, our eyes should, like our antenna should start go up, and we should think, okay, there is some random experiment that is happening. So what is a random experiment? Okay, so I mean, defining a random experiment itself is a tough job. But the way people have come up with some sort of what do you call, some sort of definition. And what that definition is, it is, people say, any experiment, okay, any experiment, uh, any experiment whose outcome cannot be determined at instance level, but has some regularity regularity at population level. Let me explain this to you. So what does this mean? Okay, so the idea is that, okay, you, whenever, whatever is a random experiment, you cannot tell what the outcome of that experiment will be at an instance level. So for example, if I toss a coin, okay, you cannot tell, you cannot say with certainty that, okay, you have tossed this coin, so you are going to get a heads. You cannot say that. But so this is an instance level thing, right? Okay, so when I am tossing a coin at for one instance, you cannot tell me, okay, if it is going to be a heads or it is going to be a tails or things like that. But let's say if I keep tossing the coin for, let's say, 1,000 times or 10,000 times, and let's say, so at after, if we, so that, this is what I'm referring to as population level. After a lot of tosses, maybe you can say something that, okay, you have tossed the coin for, so you have tossed the coin for 1,000 times. Okay, so perhaps what, 510
For
times I saw.
500 times, yeah, heads,
Yeah,
and
yeah,
500 times I saw tails.
yeah. So maybe I observed that 510 times I got a heads, and 490 times I got a tail. And and maybe you predicted something like, okay, you can tell something like, okay, actually there should be some 500 heads and 500 tails. So You know, at a population level you can say something, okay, that okay, almost half of it is going to be heads and half of it is going to be tails. But at an individual level, so if I just do one toss, you cannot tell anything, because it is a random experiment and you really don't know what is going to be the output. But at population level, maybe you have some idea that okay, I don't know at instance level. You don't know that okay, that first head it is going to be heads or tails. At second head, it will it be a tails or heads or anything like that. But at a population level, at when I have tossed it for like, 1,000, 10,000 times, maybe then you can say, okay, I don't know when the heads is going to come, but I know that half of it is going to be heads, and half of it is going to be tails. So this is what a random experiment is. Okay. So if we are clear with what a random experiment is, so okay, I mean example of a random experiment I have given you this coin toss. Okay, so let me just try and take example coin toss. Okay, so after we know what a random experiment is. Next thing that we need to define is what is called sample space. What is a sample space? And typically it is denoted by omega. Okay, so I mean again, very simple definition. This is nothing but set of all outcomes. Okay, so all the outcomes that you can possibly observe, you know, uh, uh, is your sample space. The set of all the possible outcomes is the sample space. For example, let's say you have a coin tossing example. Okay, so coin tossing, what would the omega be? Omega will be what? You have only two possible outcomes really, that is heads or tails. There is nothing outside of this, okay, that you can uh, observe as an outcome. Okay, again, roll a die. What are the set of possible outcomes? You can only have one, two, three, yada yada yada, six. Or- and there is no other face that you can see here. Okay, so I hope you will agree that the sample space depends on what experiment I am doing. There is no universal sample space. uh, what experiment I am doing decides what my sample space is going to be. Let us take some non-trivial sample spaces. For example, what if I say that okay, I do a random experiment, and the random experiment is as follows. I break a stick at random. Break a stick at random. So let's say you are given, so okay, I should have some different color. I don't know, but okay. Okay, so you have a stick. So you have a stick here, and let's say it's like some 1 meter thing. Okay, and you say that okay, you told me that sample space is set of any possible outcome. But okay, now I take a stick. Okay, and now what I will do is I will just break it at any point randomly. Okay, so I will just randomly choose a point, let's say this point. Yeah, and I will break it at that point. Or maybe I will choose this point and break it at that point. So then what would my omega be? So okay, I will check, is this experiment correctly a random experiment? Yeah, well, I mean, you are correct that if you are choosing a point at random and you're breaking it, so at an instant level, I cannot predict where are you going to break the stick. But maybe if I observe you breaking the stick, let's say uh, 10,000 times or 1 million times, something like that, perhaps I can give you some estimate that okay, yeah, most probably you are going to hit this point or break. So most probably you are going to break the stick at this point or something like that. So maybe then what I will say is that okay, maybe your sample space is really all the set of uh, you know uh, uh, real numbers that are there between 0 and 1. So let's say, I mean, so let's say this is 0 and this is 1, since it is 1 meter stick. There are several points. Let's say this was, 0.15 meter. This was at distance of 1.15 meter from the start, and this was, let's say, at some zero point 0.8 meter, something like that. So I can say that, okay, any real number which which is there between 0 and 1, you can, since you can break it at any of these points, this is my sample space. So I hope this is clear, right? That depending on the experiment, I can, come up with a sample space. It is up to me what the sample space is going to be, right? So okay, so you might then ask me that, okay, you told me this example of, breaking a stick at random. So did I even have a choice here? That, okay, is there any other sample space that
Hello,
I?
hello.
Yeah, yeah,
So sorry to interrupt. Yeah. So
yeah.
also I wanted to ask that is there any need of linear algebra to be that we need to know some linear algebra?
I think linear algebra, I think we will sail through. Okay. Yeah, you are correct. We might need it, especially when we are studying linear models. Okay.
Yeah.
But I think we will sail through it. I mean, um,
If you can recommend some kind of YouTube where lectures or any kind of lectures for linear algebra, that'd be great we, because
mhm.
I was
Uh,
thinking of getting into in depth for linear algebra as it is very also very important for robotics and all.
all right. So what I think I will recommend something. So you asked for linear algebra,
Linear
right?
algebra.
Linear algebra. Let me recommend one thing. I think you have a Gilbert Strang's Gilbert Strang lectures.
Okay, that is a
These
YouTube
are,
channel. There is a YouTube channel, right?
yeah. So there is, so Gilbert Strang. He is a professor at MIT, and he has two lecture series on YouTube. One is, I think, linear algebra for data science or something like that. Which is a relatively newer version, something around 2017. But there is an older version, around 2000s. You can have a look at. Okay, let me write around 2000s. I don't
Yeah,
remember
there is a
exactly
lecture
what.
series from 2011. I can see it now.
Yeah, 2011. Thank you. All right. So those
Okay.
lectures are quite good, but I think, I mean, we can. I was thinking about linear algebra to include it here. Okay, but then I thought that, it would be more of maths and less of ML. I agree. I agree that ML is, nothing but maths, but we need to get into specifics as soon as we can. So I thought maybe we can, somehow do some sort of. Uh, I will de-emphasize linear algebra is what I had thought.
Okay.
So.
So like for that, I would ask that if you even if it takes longer time for you to teach us more mathematics for ML, it would be great because like we have also done like model training and all, and I don't think that we have got much of intuition for ML. So like even if you cannot get dive deep into it, you in between keep giving us pointers for regarding like what should we
Okay.
learn apart from
Mhm.
what you are teaching. Like that would be
All right.
great. So like we can get a more intuitive, you know,
Okay.
intuition for
Yeah.
like.
Yeah. Sure. 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 So okay. As I said, okay. So let me just make it clear that I am not going to, compromise on maths.
Okay, okay,
That, okay. I mean, so that is the entire point of these lectures, that you cannot, skip maths to
right.
learn ML. So there is no way we are going to compromise on maths. It's just that, mathematics is tool for us. Okay, it is
Okay,
not the subject that we want to study. I
okay,
mean, if we start studying probability in depth, okay, even like 3 semesters would be less. So because
Right.
probability is such a deep concept, and the way we are taught is like very vague. Same goes with linear algebra and optimization. If we start diving deep into these things, even now I think myself, me myself, I am not very that good in these subjects. But okay, I think if you create a spectrum, okay, 100 being the most well versed person in all these subjects, I may be around 70 or 80. Okay.
Right.
So let's
Right.
just keep it that way. And
Okay.
yeah. Okay.
Yeah.
But okay, right, let us, I mean, okay, whenever I feel that okay, there is something that you guys should maybe have a look at, I will give those pointers. Or maybe if we come across some topic or some doubt that you might have which requires me to go into mathematical depth, I will do that. There's no issue.
Okay. 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 Thank you. Thank you.
All right. So okay, yeah. So coming back to what I was discussing, breaking a stick at random. Yeah. So is it fine till here? Or is there any question or something?
No, no, no,
Maybe.
no. We got it.
Cool.
Very good.
So okay, so I was saying that okay, I told you, break. It is up to me what sample space I want to create. So you might say that okay, is there any way that you could define a different sample space here? There is one way. So let us say that let me just come up with one new sample space. All right. So this new sample space, the way I will create it is the following. Okay. So this is breaking a stick at random. Oh, pardon me. Breaking a stick at random. So okay, breaking a stick at random. You said come up. You asked me come up with two sample spaces. I said okay. Well, let me come up with two sample spaces. Okay. First, I what I will do is since this is a 1 meter stick, let me create two 1 meter sticks. Yeah. So this is zero. This is one. This is again zero. This is oh well. Here is one way. Just let me keep you here. Okay. So one way I defined it already, right? So what was the first way? I said that okay, any point that I can take here in between here, any of these would do. So okay, my omega is what r 0 comma 1. Any point any real number between 0 and 1 is my the set of real numbers between 0 and 1 is my sample space. You were convinced that okay, right? You are correct. Now I say that okay, some let my brain has gone crazy, and what I will do is I will take the middle point here. Okay, I will call this as 0. And what I will do is I will go here and see that okay, I will call this point as I will call this point as what, 0.5. Okay, and I will call this as minus 0.5. And I will say that okay, I will change my convention. Okay, I will not model your stick as something from 0 to 1. I will model your stick as something which goes from minus zero point 0.5 to plus zero point 0.5. And so so you will check that okay, is it correct? I mean, will it be a problem? Well, there is no problem, right? I mean, this is correct. The naming convention shouldn't be an issue for you to now. So let's say for earlier you were saying that this is 0 0.8. Okay, now it has just changed to what, 0 0.3. So I think there's no issue. Anyways, now also it is some point between minus zero point 0.5 and zero point 0.5, and you can always uh, you know uh, what convert one system to another, and there won't be an issue. But
Right.
notice that in this case your sample space is what, r minus zero
From
point
minus
0.5.
point 0.5 to point 0.5.
Yeah, 0.5. And well, there you go. This is your new let's say sample space. So So I hope you can see that there are multiple ways to come up with a sample space. It's up to me how I want to define my sample space. There can be several examples, another example could be throwing dart, throwing
Hello.
a dart. Yeah.
But when like I my doubt is when we are like when we are when we will be calculating the possibility of the event, right? So it will be P is equals to the total number of outcomes of the outcome, the given outcome of the total number of outcomes, right?
Mhm.
So
Yeah.
what will we be taking as our total number of outcomes? Like,
Okay. So you have actually asked a very deep question. Okay. Because okay, let me come to that. I mean, I will come to those things.
okay,
You are correct. That is a valid question. That okay. Now you said that you have come up with two sample spaces, and let's say someone asks me to compute the probability. Okay.
yes,
So now will it happen that probability of this case, this case, uh, come on, probability of this case will be different from probability of this case. Is that possible? So well, I won't like that, right? I mean, I won't want the probabilities to change just because I have changed my sample space, would I?
yes,
Uh, well, it turns out that, I mean, there are cases where if you change the sample space, your probabilities will change. Okay, and probability is something that is very sensitive to your sample space. Let me just end at that. It is possible to come up with two sample spaces, right? And have two different probabilities of the same event.
okay.
uh, uh, so so let me give you an example. Let me see if I remember that example. I am not sure if I remember that example. So throwing a dart itself has a controversy to it. Okay. Okay, so how should I do it? So okay, let me draw something. Okay. Oh, so okay, just for the time being. Okay, I can expand this. Yeah. Now I think they are symmetric. Cool. Nonetheless, let us think of this problem. Okay, that you have been given. So this is a dart. This is a dart board, so to say. I have to throw a
Right.
dart at this thing. Okay. So
Yes.
basically, think of it as some sort of circle thing that is, kept at your wall, and you want to throw some arrow-like structure on it, and you want to, try to hit. You want to aim for some point, something cool. Now what I will do is, let me say that okay, there is a even smaller circle here. I don't know what. Okay, okay, fine, cool, no worries. So there is a circle in middle. Okay, and so the idea is, so basically someone comes and asks me, okay, let's say this is I am terrible at drawing. Sorry, let me just what delete this thing, make copy this thing and paste this thing here. Now it's completely symmetrical. Okay, okay, some obsession of mine over making things perfect. Cool. So someone comes to me and says that okay, here is a random experiment. I will throw a dart at random on this dartboard. Okay, and what I will do is, so let's say, let us specify some dimensions. Okay, so like this is what, let's say that this is 2 meter, 2 meter, and this is like what 1 meter, let's say half of it. Okay, and you come to me and ask me that okay, hey, you taught me all these things about sample spaces and things like that. Now tell me, what is the probability that if I throw a dart at random on this dartboard, it will land inside this blue circle? Okay, so well, okay, I see that okay, you are asking me something And the idea, so okay, so what I will do is the following. My sample space, I will say omega. Okay, so let me keep this as suspense. Maybe that is a better way. I won't tell you the sample space, but let me tell you the probability directly. Okay, what is the probability of this thing? So okay, so I will say that okay, a natural way that looks to one a natural way for me to calculate the probability is the following. So I will take the area of the blue circle,
25%.
yeah, area of black
Yeah.
circle, right? And this is what, so that pi into 1 square is pi into 1, pi into 2 square is 4, this is 1 by 4. So yeah, so as JSL correctly said, this is nothing but 25%. So there is a 25% probability that you will hit inside this blue circle. And you are okay, you say that okay, you are happy. Now I have told you some probability, and okay, your work is done. Okay, now so you go to your home, and I think ponder over this problem, and I see that okay, what I will do is I will come with an even new way to come up to calculate this probability, some weird weird crazy way to handle this probability. Okay, but nonetheless I will manage it somehow. I will manage to calculate that probability. Let me tell you how. So okay, so what I will do is okay, let me draw something. And so this is what I want to do. So bad. Okay, so I think this works. So I draw a tangent. Okay, I take some tangent. I don't know what this tangent, since this circle is symmetric, it doesn't matter what tangent I am taking, since it is symmetric. I hope you will agree with me on that, right? It doesn't matter what tangent I am taking,
Yes.
correct?
Yes. Mm.
Okay, now what I will do is okay, so this is the point that I'm trying to. So the tangent touches the circle at a single point. I hope you know that. So what will, and what I do is the following. Let me do some trickery. Okay, this is nothing but some trickery, just that. Okay, so I will do this. I take this thing, I make this line. Okay, I take this thing, I make another line here. So what I did was from this point I made two more tangents to the smaller circle. Okay. Well, now okay, now I see that okay, since the tangent is symmetric and any tangent would have worked, uh, the probability that I that you know uh, that the dart lands in this blue circle. Okay, so let me think about it once again. Am I saying this correctly? So what I do want to do with this thing is that if I uh, uh, okay, so just allow me to think over it once. Okay, let me think about it. So if I uh, throw a dart here, uh, what is the thing that characterizes the smaller circle? Okay, uh, okay, just let me think about it. Okay, just give me 2 or 3 minutes.
Okay.
I am thinking about it. Okay,
Okay, okay, sure.
so I'm just confused in one thing, that how should I define my new sample space is what I'm thinking about. So I have been given this thing, and I want to come up with a new uh, okay, how do I do it? Would it be the angle that I'm looking after? Would it work? Let me think. Okay, so I think so. Have I picked the wrong question? Perhaps I think. Okay, now I remember that thing. Okay, all right. Sorry, sorry. Okay, this is my bad. I took a wrong example. This should not be that example. I took a wrong example altogether. Shit. Let me make this thing. Okay. It should be a triangle, not a circle. That is why I was missing my point. I'm sorry, guys. I took a wrong example. This should not be that. I just came up. I was
Yeah,
just
no worries.
thinking that maybe I can give you the correct answer, but okay. So this is so instead of a circle, it is actually a triangle. Okay. Uh, my bad. Okay. So so let me specify the dimensions. So this is like 1 meter. Oh, this is 1 meter. Okay. And this is an equilateral triangle that is inscribed inside this circle. So the probability of, so okay, I mean, you can calculate that this side will be like root 3 units, root 3 meters. That is simple to see. You can just calculate what this angle is, and so you know this is 1 meter, and apply your trigonometric rules, and you can see that this is root 3. So the probability that a dart I hit will land inside this triangle is what? Area of the triangle upon pi into 1 square. Correct? That is the area of this circle. And what this triangle's area will be? Uh, so what is the area of an equilateral triangle? Half base into height, is it? Half base is root 3. And what is the height? Oh, come on. So I think if this is an equilateral triangle, this should be 30 degree. Okay. This is root 3 by 2. So it should be under root 1 minus 3 by 4. So I think 1 minus 1 by 4. So I think this should be half. Okay. Okay. So this is half, and this is another 1 meter. Okay. So this is 1 plus 1 by 2. What? 1 plus 1 by 2 is 3 by 2. I hope I'm doing this correctly. Yeah, I think this is correct. I think this is correct. So I think this is clear, right? I just calculated the height of this uh, triangle by applying simple trigonometry and things like that. This is this is the area of triangle, and pi will be the area of the circle. Is this clear?
Yes.
Can you just
Yeah.
confirm this? Okay, so what is the area then? 3 root 3 by 4 pi. This is the area. So this is the probability. Sorry, correct. This is the probability that if I hit a dart, okay, it will land inside the uh, it will land inside this thing, whatever this is. So is this okay? Is this fine?
Yeah.
Okay. Now I will come with a different way, different way to come calculate this probability. So let us see what that would be. Okay. Let me think about it. So this is again this thing. What I will do is I will inscribe a circle inside it. Let us see if that happens. Hmm. Yeah, I think now I have understood how to go about it. So can you see this smaller circle inside that I have tried to inscribe? Okay. So this is another circle that I created. Okay. And now I observe one thing. Okay. What do I observe? My observation is the following, that okay, if I draw random chords, okay, so let's say I draw a random chord here, this thing, okay, this is a random chord, this can be a random chord, it need not be parallel, this can be a random chord, Okay, so these are all like random chords that I'm drawing. Okay, and uh, so this is clear. I am just raising these chords. So I observe one thing. Okay, that when this chord, whenever the length of the chord, okay, whenever the length of the chord is, okay, yeah, whenever the length, whenever my chord lands inside this circle, this smaller circle, right, whenever this chord is, let's say, here, okay, if my chord is inside this circle, the length of this chord, let's say this is L1 and this is L2, okay, I know that L1 will be actually greater than L2. Is this is this I don't know, is this
Yeah, cause it
agreeable?
is closer to the diameter of the circle. So
Close to the diameter of the
Correct.
star.
Yeah. So this L1 will be greater than L2, correct? So yeah, I think
yes,
correctly said, as pointed out by you.
yes,
And if I draw a chord that is, somewhat like away from this thing, the middle chord L2, let's call it L3, then perhaps you will also agree that L2 is actually greater than L3. So the idea is L1 is greater than L2 is greater than L3.
yeah,
So I drew three chords, one which is a tangent to the inner circle, one that is uh, inside the inner circle, and one that
inside
is
the inner
outside
circle.
the, yeah.
Exactly. Yes.
And I observe this relation between the length of the chords. Correct. Now my argument is the following. Okay, that if I throw a dart at random, okay, let's say I throw a dart at random, yeah, the probability, okay, the probability that it will actually be inside the circle. So okay, so maybe what I should do is uh, so okay, so let's say that you ignore these two. Okay, I mean, let me just use this thing. Ignore these two sides. Okay, let us ignore these two sides for now. Since this is symmetric, okay, I think I can uh, uh, like work with this triangle in a symmetric way. So I will just for now time being just ignore the what I'm trying to say is just consider this pi. So this part of the circle is what I'm asking you to consider, right? I can actually break this circle into
Yes.
three pies, right?
Right.
This is how it works. So I am saying that okay, just for the time being just focus on this thing, just this one pi that is there. Okay, now in this one pi, if I throw a dart at random, let's say the dart actually, exactly lands in this first pi. If it lands there, and I draw a chord that is parallel to this side of the triangle, okay,
Yes.
and if its length is, smaller than this length, the length of the triangle, then it should be outside the triangle. Is that okay?
So like so if the dart represents a point, right? And if
Yeah.
I draw a chord passing through that point,
Yeah, that is parallel to this
and
side.
the distance from the center of the circle is like we should be
Yeah.
looking at the distance from the center of the circle, right? We shouldn't be
Yeah,
looking
both
at the
of
length
them
of the
are,
chord.
yeah, both of them are, yeah, you can use
Yeah,
that
yeah,
as
okay,
well.
sorry,
So
sorry, yeah, my bad. Yeah, yeah. The length of the chord should represent, yeah. So if the length of the chord is less than
it is
its
directly related to the center
yeah,
from the
yeah.
center,
Yes, 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 yes,
distance from
yes.
center.
Got it. Yeah,
So if
got
I
it.
use this,
Please repeat that again.
so sorry.
Please can you repeat that again?
Okay, so the idea is that I am asking you to, consider this pi. Okay,
Okay.
there are three such pies of this triangle. I hope you can see them now.
Yeah, yeah, yeah.
I am saying that okay, let us consider just the first one. Okay, this is this one. Okay,
Okay.
now if I throw a dart and the dart, let's say, lands here. Okay, what
Yeah.
I do is next is I draw a chord that is parallel to this side of the triangle.
Okay.
And then let, as Jeshal said, so okay, if the length of this chord, this new chord that I drew, okay, which is, let's say, this from here to here, this is the length of the chord, okay. If this length is smaller than the length of the triangle, the point that the dart that I have thrown must be outside the blue triangle. Is that
Okay, got
agreeable?
okay, got it.
So okay, so what I'm saying is that, okay, if I draw this thing here, right, and let us call this L, okay, this is L4, let's say, and this is, so this is your side S, let me call this S, and let's say I throw a dart again and it landed somewhere here, and then I again drew a chord here, this chord, and I call this as L5. You would agree that, L5 is greater than S, which is greater than L4.
Yes,
Will you agree with this?
yes, yes.
Okay,
Because
thank you.
it's closer to center, that's
So
why.
yeah, exactly. Right. So now my way, the way I, so okay, so what is, so then I ask the following question: what is the probability that in this part of the circle, if I draw a random chord, yeah, if I draw a random chord, what is the probability that, it will actually be, its distance, so its length L will be greater than S? So what I'm trying to say here is, what is the probability that length of a random chord is greater than S, is what I'm asking. Okay. Am I clear here? I am asking that I throw a dart at random, I draw a chord, okay, and then I just have to check if its length is greater than S or is it less than S, and then I can tell whether the dart landed inside the triangle or did it land outside the triangle. Is this okay?
Yes.
This is my procedure, so to say.
Okay.
Okay. So what will be the probability that a chord, has a length that is greater than S? To calculate that, what do you have any suggestions? How
Yeah,
we can
so
do that?
that will be the area of the circle. Uh, that will be area of the circle. No,
Mhm.
that will be the area of the triangle divided by area of the circle, I think. Was like
No, actually, if I am drawing chords at random, right?
right, right.
Let me tell you another way to do it. Okay, so what I will do is, since it is a random chord, right? It must
Yes,
have a distance from the center, as you were earlier saying, right?
right, right.
If this distance is greater than, let's say, what this distance is, this if this
Yes,
distance is greater than this distance, then it is definitely, smaller than S.
yeah.
And if this distance, so the chord that is inside the blue triangle, if it is in, so that distance, you know this distance is like less than this distance, okay, I
Mhm.
can use this as a metric now.
As
uh,
well.
uh, Let me write that. What I want to say is, this will be, okay, uh, uh, how do I tell it? So okay, okay, let me calculate. So okay, yeah. So this distance is what, 1 by 2, we calculated that, right?
Yes,
Yeah. And this entire distance, this big distance,
is one.
is 1, correct?
Yes.
So can I say that, okay, since I have been given these random chords, so I have been given these random chords, okay, these parallel
Mhm.
random chords, okay, I can use the distance from the center to these chords to define a probability.
Right.
What I will say is that okay, all the chords who are like here, okay, who have a this who are at a distance less than half from the center, okay,
Will
those
have the,
chords
yeah, will be, yeah,
will be inside this thing, and all the
yeah,
chords that are outside who are at a distance
will be
greater than
smaller
half,
than the, yeah, yeah,
correct. So I can
yes,
use this length as a metric itself. So I can say, so end of the day what I am trying to say is this will be one half because this distance is half, okay, half
yes,
upon this distance, the bigger distance, this distance, one.
yeah,
And since I considered only this part of the chord, right?
yeah. It will be
uh,
one third.
yeah, there are three
Thrice.
symmetric, yeah, no.
Yeah.
So with probability one third, it will land inside one of the chord, right?
Yeah.
And then the probability that its length is of the random chord is greater than s is 1 by 2. So eventually this will become 1 by 6.
Yes.
Okay, so I think I confused you. I don't know.
Yeah, but I got it
Okay.
clear that the probabilities change with the sample space, the kind of thing we are looking at.
Yeah, exactly. That is my exact point. That if you change
Yes,
your
because the
sample space,
probability over there was different, and the probability over here is different.
exactly.
And here
So
also we are finding that the diet will land in the triangle or not.
exactly,
Yes. I got quite clear over there.
yeah.
Yeah, I got
So
clear.
yeah, so you can see, right, that I mean I agree that this method that we saw here is like a like uh, there is a like it's a weird way of calculating this probability, but nonetheless it is correct. I mean, one cannot argue with me that no, you are doing it incorrectly, because all my statements were logical. I
Yes.
didn't hand wave at any point of time. But I mean, I can see that as soon as I changed the way I am calculating my probability, I got a different probability. So,
Yes.
I mean, well, you can ask, right, that okay, when the event that I am asking you to calculate the probability of is same, why is it that I am getting different probabilities? Why is it happening? So actually, it turns out that your sample space, as I earlier said, is different in both the cases. What was the sample space here? Well, in some sense, here it was a set of all x comma y pairs that belonged to R2, okay, such that x square plus
X
y
square
square
plus y square is equals to r square or 1.
less than or
Yeah.
equal to 1, because I am considering
Yeah.
the points inside this set.
Yes.
This was my sample space here. Well, what is the sample space here? Now if I think of it, my sample space here was nothing but this line, okay? This line,
Yeah.
wasn't it?
Yes.
I just
It
calculated
was,
the probability of this region that I am, circling
so
over.
that would be x belonging from 0 to r
Yeah,
radius of the circle.
yeah, correct,
Yeah.
exactly. So I reduced my question to one R1 again. So here my what was my so it was simply R again 0 to 1
0 to r or 1. Yeah.
1. Yeah.
Yes.
I think here it will be closed. I'll have to see.
Inclusiveness.
But so so did I make my point that changing the
You've
sample
made me
space?
quite. Yes. You made me very clear. Yes. Yes, I
So
never looked at it this way. Yeah.
yeah, so I mean, yeah, it comes as an epiphany, right? That okay, every time we have been taught of this traditional method, that take go for the
Yes.
area.
Yeah.
But as soon as you come up with some weird looking unconventional way to calculate the probability, this is what you get.
Yes.
But
And
nonetheless,
it
like,
also clears, that if you know the sample space changes everything. Yeah. Yeah.
yeah, exactly. But I hope you will agree that here, even changing the sample space shouldn't, bother you. In
Yeah.
this
Yes,
example,
it should
breaking a
not.
stick
Yeah.
at random,
Yeah.
here it won't bother.
Yes.
I'm
Yes.
just saying that. There is a reason behind it. There is something called sigma field, that there is a concept of sigma field associated with a sample space that is used to define a probability space and things like that. So turns out that the sigma field generated by both of these sample space is the same, and hence you are okay with it even if you change things, right? It is okay. But
I
in
don't
this
know what
case,
is sigma
yeah,
field.
yeah, I think it is a, like, again, as I said, right, probability theory requires you to do a 3 semester of coursework. First semester you
Yes.
will learn these things, and in second
Okay.
semester you will perhaps learn about something called measure theoretic probability, and in the third semester you will learn about martingales, filtration, and like even deeper concepts. But yeah, nonetheless, here, just remember this thing, right? If, let's say, you give this example, what the hell, okay, sorry. So if, let's say, in future, some you go to some person, and you try to impress him by showing these calculations, and it turns then someone asks you, why is this happening. The reason is that the sigma field that is generated by these two sample spaces is actually different. What is sigma field? Maybe I will leave it up to you to look it up and see what it means and things like that, because if I go into that, then I think I'm already late. But yeah, I
Yeah.
think that will make the case even
Yeah.
worse.
No.
Yeah.
Like, you see, when we are studying all this probability on all this stuff, intuition, I think it is very important. So, like, if you share the books, it is okay if you share the books, but if you can share the videos, no, so it will be great, because videos give, like, videos show you things that are not actually mentioned in the books, or maybe some of the words you catch on to that makes you
Mhm.
understand things more.
Okay,
Like,
so
that will be
let
great
me
if you can
mention
share
that
in the.
here. So, okay, so let me mention this one lecture series. People usually hate Neptel. I don't know if you guys know what Neptel is. It's a
Yeah,
online
NPTEL, yes.
platform
Yeah.
by NPTEL, yeah. And people usually
NPTEL.
hate
Yeah.
it because they have a lengthy lectures, and there's an old prof that is talking in front of you, and you makes
Yeah.
perhaps you sleep watching those lectures. But there are gems hidden in Neptel, and one of those gems is this one. It is by Krishna Jagannathan. He's from IIT Madras, an excellent teacher and an excellent researcher as well. He has a course on probability theory. I don't know what the uh, uh, something called, if I remember correctly, right? It's something. The name is something called uh, uh, foundations, I guess. Something on this line, yeah. Foundations, probability.
Foundations for electrical engineers. Probability foundations for electrical engineers.
Yeah, foundations of probability for electrical engineers, something like that.
Yeah.
There is this lecture, and, like, you should, if you are interested in probability theory, this example that I took is from his lecture, and I you know uh, as it might be happening for you, for me also, it was like this epiphany moment. Oh wow, what has happened.
Yes.
Okay, but okay. So maybe you can watch that. That is a nice reference material. If you do that, I think you are, that is measure theoretic probability. People, there they talk about, so it's it's a bit involved, and it's not a first course in probability. It's even bit, uh, what do you call it, it's a in-depth analysis of what probability actually is.
Right.
Okay, so so much for sample spaces, right? I have spent
Yes.
like a lot of time on sample spaces. Like I'm sorry, I came up with the wrong example, and I was trying to remember how to actually calculate it. So it has been a brain massager for me as well. So yeah, okay. Nonetheless, let's move forward.
Yeah, no worries. Yeah.
Okay, so since like okay, so maybe what we will start doing is since I want to complete this today and we are only when not we are not there yet. So okay, let me just explain things broadly now. I don't think I will be able to go by the books now, but let me tell you few things that are important and we are going to use it in ML. So okay, now we were talking about since we were talking about sample spaces, there are I hope you can now see that these examples, for example, these set of coin tossing, rolling a die, these were kind of very easy examples. Do you agree with me? Like there was nothing much to it.
Yes.
Yes, yes.
Yes.
But when we started talking about breaking a stick at random and throwing a dart and things like that, things started to become a bit difficult. So I think, I mean, so that because there is a basic difference between these two types of sample spaces, because the first one was actually a countably finite sample space. You can count the number of elements in that sample space, and that sample space is finite, so it has a cardinality. Okay, whereas the other cases were uh, uncountably infinite at omega. You can also have a this thing, right? Countably infinite, countably infinite omega. Okay, so what do I mean by this? So let me write the examples here, right? Coin toss, let me write it CT. Coin toss, rolling a die RD. Okay, uncountably infinite is what? Breaking a stick at random, breaking a stick at random, BSR. Throwing dart at random, TDR. I'm just writing these short forms, these don't mean anything. Okay, so what could be an example of countably infinite omega? So a sample space which you can actually count, but you can, but the set itself is infinite. So for this I can give you some example. For example, you know number of tosses required to get a head. So what I mean, so you are given a coin and I ask you that okay, you keep tossing till you get a head. So what are the possible outcomes, right? So you can actually have heads at the first instant itself, right? You tossed it first time and you got a head. Another possibility is that you got a tail and then you got a head, or you got tail and head. You got three tails, then a head, and so on. So it is possible that you get T like 1,000 times and then a head. Are you getting my point? So it can also happen that you get T, I don't know, like 10 raised to like 100 times and then a head. Is this am I making sense what I'm saying? That it is so it is not possible to count how many elements are here because there are infinite number of elements. It is possible that you can keep tossing and you won't ever encounter a head. So since the set of natural number is infinite, this will also be a infinite set. Is this clear?
Yes.
Am I clear here?
Yes. Yes.
Yes,
So
yes.
this is what you call countably infinite omega, right? You can count that this is okay, this is the first element, this is second element, third element, things like that. But it's an infinite set. You cannot tell how many elements are there in this set. I hope you agree with that. Okay.
Yes.
Now, I think this example that we discussed here, right, already massaged our brains with some probability calculation thing. Okay. Now let me just
Yeah.
quickly, go over some of the, probability rules that will be, useful for us, and you will be using those frequently. So the first one is like what we call is total probability rule. Okay. So now imagine that, don't know what will be. Yeah, okay. So this is your omega. So like I'm just making this thing doesn't mean that, so this is just a way to represent omega. This ellipse means nothing. Okay. This thing whatever I have drawn here means nothing. So it is just a abstract thing that I'm drawing to explain you something. But yeah, this is not omega as in this is omega. Okay, it's just a thing way to represent it. So I partition it by several segments, so to say, like these. Okay, and I call this b1, this called b2, b3, 4, b5, some bn. So if like bn, so if this b1, b2 till bm, these are what partitions of omega. What do I mean by partitions? I mean that, okay, if I take b any, for any I take bi, I take its intersection with some other bj. This is a null set, there is nothing common between these sets. Yeah. And if I take union of these bi's, this should return me my omega. This is what I mean by partitions. Okay. So I think this is clear. Okay. So what is the proposition? The proposition is as follows. If I want to calculate the probability of an event A, okay, and I can write this as probability of an event A intersection with omega. Oh, wow! For the first time, it is happening with omega. Okay, this is what I wanted to say. Okay. So, is this correct? Are you okay? Are you fine with this? Do you agree with me on this thing? I don't know. Hello.
Yeah. Yeah. Yes. Yeah.
So what I have done is nothing, right? A is a subset of omega. A is an event. An event is always a subset of the sample space. I have taken its intersection with the sample space itself. So it would be, so it's like this was your omega and this was your A,
So that would be event
and
itself. Yeah.
yeah. So that is what I was saying. Just nothing fancy here. Okay. Now what I can do is I can write this P as A intersection. I know that from this property, right? From this property, what did it go? This thing. From this thing, I know that I can write omega as union of bi's. So this is what union of bi. Okay. And by uh, so intersection of unions is nothing but union of intersections. This is from set theory. Like, I mean, what this is what I wanted to say. This is A intersection bi. So I mean, maybe if you are convinced, then maybe it is okay. If you are not convinced, just ponder over it. It's a simple thing that intersection of unions is nothing but union of intersections. Okay. And this will be what? This will be so let me write this as probability of union of ci's, where ci is nothing but a intersection bi. Okay. And since BIs are disjoint, okay, A intersection BI will also be disjoint. And we know that probability of union of disjoint sets is nothing but summation of individual probabilities, which is nothing but summation of probability of A intersection BI. Okay, does this all, is this okay? Is this fine, or did you have any doubt in any step? Uh, uh, is there any step that you had doubt in? Maybe it was not clear. You want me to, explain it? I can do that.
Yeah, no, no, we got it. Go ahead.
Okay.
Got it.
So you got it right. Okay. So now what we can do is, okay, maybe I should have taken. Okay, no worries. Okay, so let us keep this in mind, right? Okay, what I wanted to say is probability of A is nothing but summation of probability of A intersection BI, where BI satisfy these properties that I have written here, that they are, partitions of omega. Cool. Now coming to what I wanted to, the punchline. One more important idea is that of conditional probabilities, right? What is conditional probability? Uh, so let's say we have an event P. P is an event, yeah, and we have probability of this event is greater than zero. That we are, it has some chances of have occurring. Okay, then the conditional probability of another event A. Okay, let me write it. Probability, conditional probability of another event A given B is what is what we call as conditional probability. Okay, and this probability is nothing but A intersection B upon probability of B. Okay, so now I hope you will appreciate that why this condition was necessary. If this probability was allowed to be equal to zero, right, then this
Then it would be
quantity could,
undefined.
yeah, so this quantity could go
Yes.
to infinity, and we know that probability cannot go to infinity. Probability is a quantity that is between 0 and 1.
Yes.
And so probability of A intersection B is what people generally write it as P of. It's a abuse of notation, but nonetheless they write it as this thing. Okay, this is what I, this is all that is there to conditional probability. Now what we can do is, I can copy this, paste it here. Yeah, we knew this, right, from this total probability rule. We knew
Yes.
this thing. Now what we
Yes.
can do is, from here, okay, from what part of this thing, from this part, okay, what we can do is, we can write something, right? This is what we know that. So from here what we can write is probability of A intersection B is probability of A given B into probability of B. Is that correct? I hope this is fine. So now what I can do is I can take this
Yes.
summation. Probability of A intersection BI will be what? Probability of A given BI into probability of BI.
Yeah.
I hope this is fine, right?
Yes.
So in other way to write the total probability rule is, probability of any event is nothing but summation of its conditional probability into the uh, a marginal summed over these partitions I equal to 1 to n. So yeah, this is an important thing to remember. Just keep it in at back of your mind. We might use it sometime while discussing stuff. So total probability rule is nothing but just a fancy name. I hope you can see that. What it is saying is that there is some event A, and there are other disjoint events. Sorry, there are other disjoint events. BIs, something like this, something like that. Okay, and so let's say this is B1, this is B2, this is BM, this was B3, something like this. This is what, and it is saying that okay, since B partitions omega, it will also partition A, is what it is saying. And since it can partition A, we can take the information about A that is contained in let's say B1, add it. I will take the information about A that is contained in B2, take that, similarly take the information about A in B3, similarly it will be M, and I will just sum all these informations. That is what total probability rule is.
Right.
uh, yeah.
Right. Yeah.
uh, also, one thing to keep in mind is that conditional probability is also a probability. Okay, I mean, I hope it was, so it satisfies all the properties of probability that is there to be there. Uh, for example, there are axioms of probability which I skipped because in the interest of time. But the properties such as it should be non-negative, you can see why it is non-negative. It should sum to 1, so probability of omega should be 1. And there is something called sigma additivity that has to be satisfied. That will also be, you will have to verify that, but that, yeah, that will also go through, and hence conditional probability is also a probability. Okay. I am skipping that part. Those things, those are like details, but yeah, I mean, as I said, it is just a primer. I don't want to, take a series of lecture on probability theory. I want to take a series of lecture on uh, machine learning. So that's that.
Yeah.
Next
Yeah.
thing that we should, I think, discuss is what is called independent event. What are independent events? Well, there are there is a simple formula for this. If two events A and B, okay, if two events A and B satisfy this property, then they are told they are independent. Uh, they are called independent events. So basically, they have nothing in common, is what you can say. So if I take the intersection of their probabilities, so if I ask that, okay, what is the probability that both the events A and B occur simultaneously, the probability of that event is just the uh, product of the individual probabilities. That's all. Okay. Uh, then from this you can also see that probability of A given B is what probability of, we saw this thing, right? From conditional probability definition, this is what we have. And if A and B are like independent, this numerator term, what will it become? This will become probability of A into probability of B upon probability of B. And now you can see that this term and this term gets cancelled, and this is just probability of A. So like, I hope, I mean, as I said, right, that if by intuition also we could have said this, that okay, if two events A and B are like independent, they don't depend on each other, it doesn't matter what information about B I have, it would provide me no additional information. Okay. So
Yes.
okay, so let me just ask you one thing. Are you guys bored, or is this okay? I mean, is this going fine, or I mean, I just want to take
No, no,
some
it is
occasional.
going fine. Yes.
Yeah,
It
fine,
is
fine.
going fine.
Okay.
Yeah,
So
okay.
We are just
if you
very
think
focused. So.
yeah, yeah.
if you're just
Okay,
very focused.
okay. So occasionally what I will try is I will try to give you some fun stuff. Okay.
Yeah.
So here is one fun stuff. Okay. Uh, Let us talk about causality. This is something that I was reading, and it came to me that okay, I mean, it came as a surprise to me. That's all. Okay. So what is it? So the idea is following. Okay, let me not give you the spoiler. Let me first ask you something. Okay, so if I write this following thing, right? Probability of A given B. mm, Probability of A, okay, probability of an event A is greater than, let's say, probability of A given B. Or I mean, let me reverse it and write it. That would be more clear. Probability of A given B is less than probability of A. Okay. So what I am saying is that okay, here is an event A and another event B. Okay, and someone comes and tells me that okay, you know what, the probability that A occurs given that B has already occurred, okay, is less than the probability that A would occur. I mean, in some sense, some information about B. This can be seen as some information about B that I have. Given this information, the probability about uh, probability of the event A is actually less than the probability of A if I had no information about B. Okay, this is what this statement is saying. So now, does this mean that B causes A? Did you understand my question?
Can you please repeat it?
Okay, so this is the statement. Okay, this is the statement. Is this statement clear? Is there any ambiguity in this statement?
No, it is clear.
Okay, now what I am
I
saying is
still
that
sorry, I'm not quite clear. So
so there are two probabilities. Okay, one is a conditional probability conditioned on an event B. Okay, and there is another
yes,
probability which is a unconditional probability. Okay, it's just the probability of the event A. And I am
yeah,
saying that, well, this probability. So okay, let me just tell you. Would you agree that if I had removed this condition, you would have this probability of A should be equal to probability of A? This is correct, right? I mean, this is trivial. This is trivial, is what I am saying. Correct? I mean, probability of an event won't change. It is what
yes,
it is. But as soon as I do a conditioning, as soon as I condition it on some event B here, okay, this probability it
yeah,
becomes lesser than the RHS that I had here.
yeah.
Okay. So does this, in some sense mean that, let me give you an example. Okay. Let's say there are, two events. For example, an accident happening. Okay. Correct. And
Right.
the driver increasing the speed of the car. So yeah, that is, I think, a fair example. So you can think of A as accident and B as speeding up. Okay. So this is what I am saying, that okay, the probability that the accident occurs is greater. Okay, no. Uh,
So like it should be slowing down.
okay, okay, yeah, it should be. Yeah, yeah. I think. Sorry, just let me make this thing here. Yeah, I think this should be what I am trying to say. Yeah,
Yeah.
yeah, yeah. Correct. Now it makes sense, right? That probability of your accident happening. If so, the probability of your accident happening if you are speeding up is greater than probability of the accident itself. is what I'm saying. This the statement in words actually makes sense, right? I hope you agree with that.
Yes, yes.
If you start speeding up, there is a higher chance, higher probability that you will encounter an accident as compared to you don't know anything about what you are doing. Maybe you are, if you are
Yes.
driving at a low speed, then there's a fairly low chance, and you don't know anything, so it's a lesser probability, things like that. So does this mean, so someone comes and tells me about these things, okay? So now my question is, this does this imply, does this mean that B quote unquote causes A, question mark?
Yes.
Yeah, it does
Yeah, yeah. Now I
look
get it.
like that, right?
Yes.
So I mean, will you agree that conditional probability actually tells you something about causation in some sense?
Yes.
You know,
Yes, yes, yes.
if does everyone agree? Other people, I don't know. Is Jeshal, some monitor or some kind of leader? I don't know.
Yeah, no, no. Yeah, no.
Nothing.
So this statement is clear, right? Okay. Well, surprisingly, okay, this was a tricky question. The answer is actually no. Answer is actually no. Well, why? I mean, this does look like a good argument that if I have information about some event B, and my probability of an event A occurring increases, then perhaps B should in some sense help in the event of A happening. This should be the thing that might be going at the back of your head. Does this make sense what I just said, that some
Like
information
how
about
this
B? Yeah, yeah.
uh, does this means that
Let me write in words, maybe I'm not articulating it correctly. What I'm saying is, this gives an impression that B increases the chances of A occurring. This is what I wanted to say. That if if I know that B has happened, if I know that the driver has speeded up his car, then I can say that there is a larger, higher chance that he will encounter an accident. I mean, this statement in some sense gives us that impression. Does this Am I clear?
Yes, yes, yes.
yes,
Well,
yes.
now let me do some trickery now. Okay, so what I just said was, let me write some maths. Given B is greater than probability of A. Okay. Now, from this definition of probability, right? Conditional probability. What is this? This implies probability of A um, intersection B, probability of B is greater than probability of A. Is this correct? I hope this is correct. Uh, then what I can do is I can bring this here and bring this here. This is what probability of A intersection B upon probability of A is greater than probability of B. Okay. Now this means that, okay. Now I hope you can see that this thing that I have here now, okay, whatever this thing is, this is nothing but probability of B given A. Is this did you get this point? Maybe mull over it, think over it, what I just wrote. So let me tell it once again. This is the definition of conditional probability. Yeah. And what I did was shifted uh, like
Yeah, yeah,
took
that I
this
get
here.
it, but like, what are you trying to convey with this? Like,
Yeah, so okay, what I'm trying to convey is the following, that t of a given b greater than probability of a also implies that probability of b given a is greater than probability of b. So if you, okay, let me keep it here. Let me write it in statements. This we were interpreting as b causes a. Okay, this is what we were interpreting this as, correct? And this, what this tells us is a causes b. I hope you agree with me.
Yes, yes.
So if I, if this statement is true, then this statement is also true. In other words, what I am trying to say is, if you say that b is causing a, well, then you will also have to agree that a has caused b. So if you are, I mean, in this probabilistic sense, if you say that accident has happened because the driver was speeding up, then you are also saying that the driver was speeding up because he encountered an accident.
yes, yes, yes.
So I mean, this is a weird thing that you see, right? Again, I mean, again, some weird thing that you thought that okay was correct, but in actually it's not. So what the punchline? The punchline is the following: conditional probability conveys nothing, nothing about causation. Okay, so this was like one thing that I wanted to convey, that it might look tempting to interpret this as some sort of causal thing that is happening, but well, that is not correct. And you are not making sense actually if you say that, because you're saying b causes a and a causes b at the same time, while this, it is not possible that you know two events are causing each other at the same time. It's like doesn't make sense.
Right.
I don't know, was I able to convey my message or not? I'm
Yes,
not
yes,
sure.
yes, yes. Yes, I'm clear now.
Okay. So I don't know, I mean, the first time I saw this, it felt that, oh, well, I mean, when I saw this, right, this thing, I thought that, yeah, it does mean that some information about b helps me to predict a better, is how I interpreted it. And so b must be helping in some sense.
Yeah, B must
It
be like
was
boosting up, like it will be boosting
the
up our,
chances of a.
yeah,
Yeah,
yeah, yeah.
but if you say that, then well, A is also boosting the chances of B. How
Yeah.
does that make sense, right?
No, yes, yes. Yeah.
So again, so what like the punch point is the following: that conditional probabilities and probabilities in general are just numbers. Okay, they are
Right.
they are like you can manipulate them to uh, come up with weird looking things that don't make sense.
Right.
Okay, like this one. Okay, so just
Yes.
these are just numbers, and in some sense it gave you idea of causation, but actually it's not that.
Right.
Okay.
Yeah.
So I think independent events are done. Okay, so what is left? So maybe Bayes rule is something that I haven't told, right?
Yeah.
Okay, so maybe I will write out Bayes law. Bayes rule. What is Bayes rule? Bayes rule is, I mean, Actually, it's just an extension of the definition of conditional probability, which was what probability of A intersection B upon T of B. Yeah,
Yeah.
and I can. Uh, okay, so now let me write another thing. Probability of B given A is what? Probability of again A intersection B and probability of A. And from here we can write probability of A intersection B is what? Probability of B given A into probability of A. Okay, now if I substitute this thing here, what I will get is that this is what probability of B given A into probability of A by probability of B. So this is the like the Bayes rule. Yeah. uh, the common form in which we use it is this, right? Probability of, let's say, x comma y is nothing but probability of x given y into probability of y, which is also equal to probability of y given x into probability of x. So this is I don't know how, but this is, you should just keep this thing in mind. Like, this is something that we will keep using, like while sleeping you might be doing these calculations in your dream. So this if someone tells you something like this, you should be able to break these things, and you should not be surprised that how it has happened. Okay. That is what I wanted to.
You mentioned that P of x comma y, like x comma y here is a
Yeah, yeah.
function, or it means x
No.
intersection y.
So whenever we write this probability of something comma something, right, it means probability of x intersection y. That's what we mean.
Okay. Okay.
So it's difficult to always write this intersection. People said that, well, let us remove intersections and just write it as something comma something. So the way to interpret this is that, okay, x comma y both are happening at the same time. That is the intersection of these
Intersection
two
of both
is what.
events. Yeah.
Okay. Well, and now what? No, it's just manipulation. Now we can do some manipulations, and basically what we showed here was probability of A given B was what? Probability of B given A to probability of A upon probability of B, right? Now from total probability law, okay, what we said was probability of B can be written as summation of probability of B given Ci. I goes from 1 to m, where Ci's are partitions, right? Okay, we know this from probability total probability law. Okay, now one obvious partition that you can always come up with is an event A and its complement. Okay, so we know that A intersection A complement is what? Phi. It's a null set because both are complements of each other. And we know that A union A complement is what? Omega, right? So these are
Hello.
like,
Uh, Sorry, but here summation of probability of B by Ci, shouldn't be B by Ci times Ci?
oh yeah, sorry. Oh, right, correct. Oh, I'm really sorry. This is, thank you. Yeah, correct.
Yeah.
So the my point that I wanted to convey was, A and an event A and its complement are always a valid partition. So I can
Yes.
always, partition omega with A and A complement, and using that, what I can write is, this is like the numerator will remain as it is, probability of A. I can actually, modify the denominator now. What will this become? Probability of B given A into probability of A, yeah, plus probability
Yes.
of B given A complement into probability of A complement. This is like just another way to, write the Bayes rule or whatever you call it. Yeah.
Yes.
Okay, is this like clear?
I still don't get the point why.
Uh-huh.
No, I know, I get it. Yes, but
So what I
shouldn't that
wanted to
lead
say
to
is that
two times of P of P? Won't that lead to twice of P of B?
no, no, no. So what I want, so okay, let me write this. So you agree A and A complement are partitions of omega, right?
Yeah, that I get it.
So what I can, so using this, whatever this we had, we can write this as P of B given A into P of A, right?
Yeah.
Plus probability of B given A complement to probability of A complement.
Okay, no,
So
no,
I
no,
am,
I got it. I forgot about the summation, but no, I get it. I get it. Sorry.
so I have
Yeah,
just substituted this thing here, okay?
yeah. No, no, I get it. Yeah, sorry.
Hmm.
That's right.
So Bayes rule independence, I think we are like more or less there. Like I wanted to finish probability theory and start something then tomorrow. Uh, okay, so I think it's 7 p.m. and I like, don't want to stretch it.
Okay.
What we can do is, I think it's it might be becoming heavy for you as well, uh, because I don't know, sitting for 2 hours is a difficult task. I know it firsthand. So
Uh-huh.
yeah, so okay, so let's end this here. Okay, yeah, that
Yeah,
is, I think it's a good stopping point.
right.
So, okay, so what is the plan for next class? Let me just make a point here so that I am ready. Okay, so what do I want to? So the things that I think I should cover here next time is expectation. No, before expectation, I think there will be common distributions and densities. Okay, then we should have expectations, expectations and conditional expectations. Okay, then I think we should go into info theory, and then should I think perhaps I should pitch you the MLE. Let's get
Uh,
started.
so the last time you started with the lectures, you guys went on with Gaussian filters and all. I don't quite remember what was that. So like,
What?
won't we be covering all of those things here?
Which thing? Which things?
Some Gaussian curves you look into while I was
Yeah, yeah.
talking about some Gaussian curves and all.
Okay. So I'm not sure what he was, teaching, but uh, uh, Gaussian and all those things will come here in common distributions and densities. We will discuss those
Okay,
things, Gaussian and like new
okay.
distributions. But yeah, so uh, I think we don't worry. We will do that. We will discuss expectations and conditional expectations. Will
Because Gaussians and all was very, it was very tough for me because
Gaussians and all,
honestly,
huh?
yeah, because I honestly have never studied probability theory with much interest and, I've only studied it for the academic perspective and didn't get much into it. So,
Yeah, yeah. Yeah, don't worry. I mean, we will discuss those things. Yeah.
yes.
So in info theory, I want to cover entropy. Entropy is a good starting point. Then we should go to KL divergence. And then we think mutual information. I think here we should stop. Okay. I think only these we will be able to cover these three things. I think with the knowledge of these three things, we can start with maximum likelihood estimation. And yeah, I think I can show you a few things there. Let's see what how much we are able to cover in the next lecture. Okay.
Right.
Okay. So yeah, I
Sure.
think let me just stop the recording first. Yeah. I hope there is no doubt, so we can stop. Yeah.
No, no.
So let me just stop the recording here. Thank you.